Hey, Justin, are you on the stream or are you on Zoom?
I'm on Zoom.
Okay. I nominate you. Kick us off. Are we all ready to go?
Ready? Any nays? Today we have Stuart Small come to us all the way from the great state of Colorado to talk to us about building malware in Rust. Take it away, Stu.
Cool. So I want to give you all a little bit of background about myself. I've been in the security industry for a few years. I came here through a lot of embedded systems in the past. So I've got a strong background and a lot of C, and that's going to come up a lot when I'm going through this. My last job was at a company called ThreatX. We were using Rust almost exclusively. I think at the time I left, our code base was about 80% Rust, and we were phasing out some old Python APIs. We originally wrote our WAF in Rust and found out that it just worked really, really well for a lot of the stuff that we needed to do. So we started taking on a lot of server-side APIs in it. And while I was there, I really fell in love with the language. When I initially took the job, I was super skeptical because it was, I think Rust had hit its 1.0 not even a year before I started there. So it was just a brand new baby language. And it had some rough points. It's grown up a lot in the 5 or so years since then. So I've recently taken a new job at a company called Randori. Our focus is attack automation. We're a red team for hire for companies. So if you have a large organization, you want to test your defenses, help train your internal blue team, we're there. We will watch what you have, break in where we can, help you see the path of what went wrong, how we got in, and help you remediate the issue. So this is my first time ever stepping into a place where I'm going to be writing malware. In the past, I've written exploits, I have done pen testing, but never anything where I care about getting persistence on a box, staying there, and leveraging that into other steps. Normally, I have a pretty narrow focus on what in the system's under test. So this is kind of new to me. And so I decided to step back and I'm going to learn how to do this in my own time, instead of picking up malware we have at work, but write my own from scratch. So we focused on something called an implant. This is something that's used post-exploitation. So let's say I've broken in, I have shell on a box, and I want to make sure that I'm able to stay on it and be able to come back in later, or get a good foothold so I can continue moving laterally through the network. You drop this on there, and it's going to be able to give you a shell, be able to give you file access in there, hopefully hide its tracks a little bit, and just to give you a safe point. So let's say you get evicted from other parts of the network, hopefully your implant stays on there, maybe ends up in some of their backups, so it gets rolled up, back out, and you can get back in the network through this implant, even after they've covered up the holes of how you originally got in. So they're often written in C, but they can be written in all sorts of different languages. There's some really popular Go ones out there on the internet. There's some open source Python. I saw a PowerShell one not too long ago. I decided to do one in Rust. That's what I've got the most experience with. I know really well, and it brings a lot to the table for this. And I'll get into what it brings to the table and what it does poorly. But I wanted to dive into, since not everybody's going to be used to this world, pick an open, a malware that exists out there that fills this niche, and kind of dig into how it works, why they made the design choices they did. And luckily, recently, the NSA got a hold of a GRU implant, and they documented everything about it, down to the T, what their wire protocol looks like, what libraries are used inside it, how the different services behave to each other, all the way back to, and this is where it starts getting interesting, they started documenting internals of the network of how the command and control side is set up. what kind of database they're using, how that's configured. And that's kind of one of those signs of this isn't something they just found on like, doing incident response. They actually had control of a GRU network and were documenting the internals of that. And they don't ever go out and say it in the document, but they make it very, very clear of like, hey, we were very deep in your network and we know how this worked. And it's like it's a really interesting, like kind of intercontinental middle finger from one side to the other, and like in the form of a very dry technical document. So in this, they called it, I'm not going to try and pronounce that word. It's a loose trust translation to like wood chopper in English. The way they named it is they are able to find this mentioned inside the binaries that they recovered. And so that's how they gave it its name. It's made up of a few different parts. So I'm really going to be focusing on what they call the client, and that's the implant itself. But along with it, I kind of want to look at, am I sharing my screen? I just realized I am not doing that. I am sorry. There's been slides going on. This is, oh, the world of doing everything remote. It's like, am I sharing my screen? Can you hear me? Oh, I'm double muted. I'm sorry. All of those things. So I'm sorry about that. So, and now you can see the word I'm not going to try and pronounce. That I will just refer to it as the implant or the malware from here on out. So in here, they're showing kind of the four major components that they documented out. So we have the client, which is the implant itself. And that's the thing that I'm talking about, and I'll be talking about later points. But since they're a very well-funded organization with a lot of money and a lot of manpower, they can do a lot better job than like some dude in his off hours and nights and weekends. So there's a lot more that goes with theirs, and it does a lot more cool stuff. Along with it is a pretty well-polished kernel module. And that's used for kind of like masking covering its tracks. They're able to tell the kernel module, hey, these files here or these sockets, don't report this to user space. So if someone runs ls, the kernel module is going to be scrubbing that out, and that lets them kind of hide a little bit better. And then there's the server, which is from here on, I'm going to just refer to C2, which is command and control. It's where the actors, if they have any orders that they want to give out to the client, say, hey, run these shell commands, start pulling these files, open a VPN connection back. That's all going to be handled through the command and control system. And then finally, they have something they call the agent. It uses kind of a helper to with file transfer and setting up some of these network connections. It's kind of not too interesting, it seems like, and in the documentation they didn't cover it too much on like reasons why they did it. It just seems like it's like a helper thing for when their operators are working in a network. It just makes it easier to flow through there. So like I said, they document everything about this. When this the client first comes up, it's going to phone back to the server. And so the server may not, it doesn't have to know that this client has previously existed. So there's going to be an initial sign-in process, or an initial login process, which is going to say, hey, I'm here. Here's some basic information about me. And then they'll use that to negotiate a secret that it identifies itself with in the future. And once that secret is negotiated, the client is actually going to reach back into itself and edit its own binary to include it in there. So one of the things that's unique about like writing malware that like server-side software, consumer software, you don't want to do this in, but it's really important in malware, is you want everything packaged in one file. You don't want configuration to possibly get lost or get away from you, or it's really easy for someone to grep and find. So often what will happen is there's a baking process where any information that's needed will actually be written straight into the binary as a step after compilation. For this example, what they wrote in there is they have a public key for the C2 server. There's a username and password that's unique to that. They implied it's unique. I actually don't know if it's unique, but it is tied to that implant release, and then a way to find the C2 server. So when the implant actually comes up, it's able to read these values out of its own executable and then go connect to itself, or go connect to the C2 server. And then once it's connected, it's established a connection, and then it has a secret provided back to it. It keeps up a persistent WebSocket connection, and it's ready for kind of any orders that we want coming back from the C2 server. So they document almost everything in here. This one is one specific module. It's their kind of file IO. It gives an operator the ability to open files, read the contents, write to them, manipulate them, move them around. Basically anything if you're working locally on a box, it gives you the ability to do that and to be able to communicate like the exfil back. And so this is an example of kind of a file download. Is they're going to start the connection, send down an open, they hear back, open success. They're going to say, hey, read. And then we start getting the data sent back up, and it's closed. Kind of like how we would expect this to happen, but we're doing this over a network and over this C2. And by providing a lot of these like kind of, I'll go back to that. Oh, that is the wrong key to go backwards. By providing a lot of low-level messaging so people can play around with it, it's going to give the operators a lot more freedom. If they think of something that they're going to want to do, they can string a lot of these low-level commands together and figure out what they want to do and be able to think of stuff on the fly without having to update the implant. Because obviously the actors aren't going to have easy access to these things, so you're not always going to be able to update them easily. So one of the other
probably should have. I'm sorry for interrupting. Probably should have asked you this in the beginning. Someone did ask a question, and so do you want us to kind of interrupt you and kind of filter questions to you?
Yeah, please do. I would love for this to be like a back and forth, and I may kind of skip over some really important details. So yeah, I would appreciate interruptions.
Sure. So so we have a question of why WebSocket versus, say, a pattern of DNS requests or something more sneaky like hiding in plain sight?
That's an excellent question. That's something that really stood out to me on looking to this one. I thought it was really strange that they picked doing this over WebSockets, especially with the budget that they have. It's not a normal thing you're going to see. And like DNS, you called out, that's a really popular one to do. Later, I'll be covering like ICMP. C2 can often happen over that. And sometimes just plain HTTP. I really thought it was interesting. And in looking at this and looking at how well funded this was and how polished it was, I just thought it was a really strange pick. So that's a great question. So one of the other really important things that they have, that they provide in theirs, is a way to be able to forward network connections. So let's say I'm an operator, I have an implant on a network somewhere, like we've infected someone's desktop, and I want to start expanding out from there. You're not going to want to drop all your, because you're the GRU, you have access to a ton of really good zero-day exploits. This stuff costs a lot of money to create. You don't want to just drop this on the file system where incident response can pick it up, or it might set off flags with some kind of like client side, like antivirus or anything. So often you're going to have your exploits or your pointy end or anything malicious, you're going to be running on your own machine, and you're going to route that traffic In this case, they route it through their agent, through the C2, down to the client, and then out to the rest of the network. But in general, you're going to want to somehow be able to route traffic through this implant, so you're not just dropping valuable zero-day or exploits onto a hostile network where someone's going to pick it up. So that's another thing, and they spend a lot of time documenting how they do that. Just kind of leave it there that they do that, and it's something. This is a normal thing, and it's very valuable. So now, do we have any more questions on that part of like how their implant works? And I will Slack out a link to that that documentation too. But I'm happy to answer any questions on how that one works or design decisions that they've made as best as I can guess.
No other questions at the moment, at least in the chat.
Cool, awesome. So yeah. Now we're at the point where I'm like, I want to build my own. I want to start from something from scratch, and Rust is what I know really well. So at work, we really heavily use C, and I've used C a lot in the past. I enjoy it. It gets the job done. There's certain things you have no other option for, and it's kind of the best answer. And so I wanted to do this one in Rust, because a lot of the things that used to be, you could only do this in C, you can now do it in Rust too. Not everything. There's a few things that are still really difficult to do in Rust. Some people may say you can do it, but it's not as practical. So one of the reasons why Rust scratches the same itch is you don't need any kind of runtime or garbage collection underneath it. You don't even need the standard library. You can strip that out if you want. And so then you can have this embedded. So like I mentioned, one of my past jobs was the web application firewall. And we originally implemented it as a Nginx module. And at the time, pretty much the only answers for doing Nginx modules were in C. But luckily we could pick it up pretty easily in Rust. We had to write a thin layer to translate the C to the Rust, and it let us be able to move really, really quickly, and with a lot more confidence than we would have in C. So one of the big things that I love about Rust is just like the quality. And a lot of people on the internet you always hear about it, people talking about like the performance. Rust is really, really fast. It's just as fast as C, and that's cool. Most of the time, you don't need that much performance. You don't need that speed. But you always, no matter what you're doing, you always need quality. And that's something Rust brings to the table, is for lower effort and costs for the developer, you can just reach a level of quality that is very difficult and takes a lot of time to reach with C. So some of the stuff that's just built into the language itself makes it easy. Like there's documentation tools that are built in from day one that makes it easy to document your project, make really good looking documentation that you can share inside the office, on the internet. And these third-party tools exist for C, and some of them are good, but I really haven't seen any that meet the level of quality that Cargo Doc does. And another thing is I've tried to get into better testing on my C code, and I've often kind of fell down on it. Either the tools are really complicated or they're awkward and lead you to a weird architecture with your C, or it ends up something pretty highly coupled and you can only do higher level acceptance or end-to-end testing. And it's a little harder to do unit testing. And with Rust, you're able to build in some of the abstractions where you can do really great unit testing. It's got a great unit test tool, like Test Runner, built in. It's got a great benchmarking tool, so it makes it really easy to pick small parts of the system, get reliable benchmarks on them, and tune them. I mentioned fuzzing is something that, I tried to get into a lot and see, and had mixed success in it, but it's so dead simple in Rust. Like the availability of fuzzers, there's 3 that I regularly switch around. First time I used it, I kind of sat down in a coffee shop. I picked a project that I'd always been like suspicious of that was we used heavily at my work at the time. And I think it took me about 15 minutes to get it hooked up to a fuzzer and found like real valuable exploitable crashes with it. And eventually I just kept, oh,
Could you
excuse me.
explain what a fuzzer is?
Oh, absolutely. I'm sorry about that. Yeah. So a fuzzer is, it is a tool that lets you feed random input into a program, and then so that is at the general case of what they are. But more advanced ones will let you monitor through profiling how the program behaves. So like often it will watch coverage or like where branches are taken as this random input is fed in, and it will mutate the input, trying to get wider and wider code coverage of your project. And so the advantage of this, especially in like C code bases, is you're just going to be throwing all this crap at the wall, exercising all these weird code paths until eventually it's going to find one that's going to trigger a seg fault or trigger some kind of crash or negative behavior in it. And then at that point, bam, you got a bug and you have a reproducible input into your function that you can use to trigger it, and then you can go fix it. They're really valuable tools, not just in like C code bases. You can use them in higher level languages, and I I've started making them as a regular thing that I use, because you can find like real valuable bugs of like, okay, if I hit these weird cases, bam, it throws an exception that's not handled. And for the what's really nice about them is when you have one that works well and it's easy to set up, and once you get it set up, it's almost no developer cost. You just have a machine running, beating your code up, and then it will find valuable bugs that you can go in and go fix later. And it'll also find a lot of stupid bugs that don't matter, that will like never be exercised or never be valuable. But yeah, I think they're really great for that. Um, and so and just kind of elaborate on that more, some recommendations on some ones that I really like. For Rust, my favorite one is a tool called libfuzzer. It's the default fuzzer that comes with LLVM. And so it's the same library that you're going to be using on like a C or C++ code base. But and this will be a recurring theme. There's a lot of overlap in the C and C++ world. So a lot of tools that you're used to or libraries that you're used to, you can easily use in Rust, and kind of get going. Another really valuable like quality tool that I've made a lot of use of in Rust is a thing called a prop tester or a proposition. Actually, I think it's proposition tester. I always just hear them called prop tester. I don't actually remember what the full long name is. But the idea there is, once again, it's going to feed random input in, and then it's going to check some proposition about it. So a common example is if you have an action or a method that should, if you run it on data and you can reverse it with another function call back to the original input, then that should be a proposition that you can run function A on the input, and then you should run function B, and then you should get the original input, which I've never in my life, like that's always in the examples for the prop testers, but I've never in my life have I come across a situation where I'm like, yeah, I can actually do that. Like this is a realistic thing. Where I have used it is a while back, and this will kind of show the like twisted mindset of the things that I do for fun. My hello world for Rust was a implementation of the Murmur 3 hash. I was just using it a lot. I was like, yeah, I bet I could write that in Rust. And so I did, and it was a lot slower and just generally worse than the original implementation. But it, it helped me learn the language, and I posted it online on GitHub, and people started using it. And then somehow it ended up in some distributed database, and like they hit a bug with it, and I got a bug report. I was just like mortified that I was not handling Unicode characters correctly in hashing. And I was just like super mortified that I got this bug report, and like people were using it and counting on it, and it kind of screwed up on them. And I imagine that that was like kind of a difficult bug to chase down, of like, oh, why are these hashes not matching up? Oh, it's this crappy implementation of a hash algorithm we were using. So in come prop testing. It lets you, in this case, I have an input. It's a random input. I can feed it in my Rust implementation, and then I feed it into the reference C implementation, and then you compare the output to see that they're the same. So then with that project, I can just run, tens of thousands of iterations and get a pretty good confidence that it's like, hey, yeah, this is correct. So yeah, once again, it's just another really cool tool that's like out in the Rust ecosystem, and it's just so much easier to use than I've seen in other languages. And another thing that really helps the world of quality in Rust is static code analysis. So static code analysis are a class of tools that will look at your code statically and try and find bugs in it. They're often called linters because of a program called lint for C. They're I've had mixed success with them over the years. Like, not all static code analysis tools are created equally. Some are good. Some of them I just spend a lot of time fixing warnings that are nonsense, that never would have like turned into any kind of real actionable bug, but I just want to get it out of the way to make the linter happy. Rust has a lot of functionality that I would normally expect out of a high quality, high cost C or C++ linter is just built into the compiler. And it's just to have your build pass, like you need those things under lock. So things that a C linter is going to look for is like a use after free or a double free, or a buffer overrun or things like that. And a lot of these things are built into the type system and are built into the compiler. So they're going to be caught right away. And they're required to be caught just for your build to pass. And then on top of that, they have additional more pedantic and picky checks in a external tool, which I love. It's called Clippy, because it's like they're like polite little nudges of like, hey, did you really mean to do this? And some of them are just super pedantic nudges, but a lot of them, it's like, oh yeah, that's actually a real performance issue, or this is a real code quality issue. And yeah, I've just had some really great luck with the linter, and it's really helped clean up my code bases more than I've seen in some other languages. And yeah. And so one of the other things, and I'm going to dive in deep in this, and it's usually the first thing that people hear about Rust, is there's a concept of ownership, and it's how the memory model works. Later in the conversation, I'm going to be doing a tour of Rust, and I'll talk about like how ownership works at a really high level. But it's what this concept of ownership and borrowing is what part of what enables a lot of these really powerful static code analysis and compile time checks, and that help keep you out of trouble. And so finally, one of the really big things that I love about Rust that it does for quality is there's no concept of null. There's no null pointer, no null references. Because like even in safe languages, I'm often hitting null pointer exceptions because I'm a garbage programmer and I write garbage code, so it's going to happen. But Rust doesn't allow that concept. It's not built in, and it's like still kind of frustrating that we're making new languages with this like same mistake that we've been making for a long time. But Rust builds in constructs to allow you to still do the same work, but there is no null. You're forced to handle, okay, this is a value that could be there or might not be. I have to handle, yes, it's there, and no, it's not. Or I made a call and this could have succeeded or it could have failed. And I have to explicitly handle the case of yes, this worked, and no, I have to explicitly handle the error. So it it means more work for the developer at first and more upfront costs, but in the long run, you're a lot more confident about the work that you're releasing. At ThreatX, we saw so many less bugs coming back, and like our quality was higher, and so because of that initial effort up front in quality and through fighting through the compiler just being like sometimes cruel, just like, please let this build pass. I'm sick of this weird borrow issue you're complaining about, or like, what does send even mean? Which I will cover later what send is. But because of that, once we shipped it, we got less bugs back. We got more work done. Overall, our velocity was quite a bit higher because of it. That was a long time on one slide. So next, I can't say that Rust has a good ecosystem. It's got a fairly decent one. It's growing, but it's a baby language. It's been 1.0 for 5-6 years now. So there's a lot of libraries, and there's often, I'm sitting down to do something and it's like, okay, what's the state of like PDF parsers? And they exist. Maybe it's not good. Or I remember I wanted to use a certain service queue, and I couldn't do it because at the time there wasn't a AMQP 1.0 implementation. There's only like a 091 implementation. It's just like, that's a shame that like these libraries don't exist. They're growing fast, and it depends on like what you're working on. The state of libraries are going to be a lot better in some places and not others. Generally with more like modern and open source tools that you're interacting with on the server side, there's starting to be a lot more drivers that are out there and libraries for it. And when all else fails, and this was very true in the early days, because it's so easy to pick up a C library and wrap it. If you can't find the library natively in Rust, but you can find the C one, it's not going to take you long to be able to call that C library from Rust. So I had mentioned earlier that Murmur 3 implementation that I'd written, and the issue with, I hit that bug and I wanted to be able to test my version versus the C version. That took me probably, I don't know, I would say probably about an hour to get that tied together. There's a really powerful tool called BindGen. You just provide it the header files and it will generate all the Rust code that you need to be able to pull this library in and run it. It is, I had read multiple times of how cool it was, and I honestly thought it was BS. I didn't think it could work as good as the hype until I used it. And I was like, oh yeah, no, this works great. Like the code and the bindings it generates are kind of gnarly. Usually you just have to put an abstraction layer over it to deal with kind of some of the unsafe C idioms leaking out, but then you're off to the races. It's really impressive. So that's something that kind of helps deal with the shortcomings in the ecosystem. But it's definitely there. Next slide. So cool. The rapid development. So this is one of the things when you're talking about, and before the presentation started, we've kind of covered on this is, is Rust a good choice? And it's like, what are you comparing it against? So like, if you're planning on building a project in like C# or Python or something, maybe Rust isn't the best choice for you, because like it's it's not going to bring a lot of the same things that these languages bring to you, of like this robust ecosystem. You can work really, really, really quickly. But if you're comparing it to C or C++, oh my gosh, like in this day and age, I can't imagine myself starting. There are a few situations where I'm going to start a new C application over Rust. Just because like from startup, I'm able to start working with like very high level idioms and get my job done and act. In a lot of ways, it's going to feel like a higher level language. Often it feels like Scala to me. I don't know if there's a lot of Scala developers in the crowd. And and so I'm able to get the job done quickly. And if I have to come back and do like lower level optimizations, or I have to do something like really close to the OS, like those options are still there. And I'm not boxed in. I'm not limited from them. But it lets me just get the job done really fast. And I definitely ran into that a lot on this project. So when I started out on this, my original plan for C2 is I wanted to do it over ICMP or ping, because you're able to pack 64, I believe 64K of information along with each ping. And I was like, yeah, I'm doing everything in that. I ended up pretty much down in the weeds. It was a lot of low-level programming because there wasn't a lot of great ICMP libraries out there for Rust. So it was working against like the C standard library through Rust, and it was slow going. And I was like, this isn't the best use of my time right now. I need to get going. I want to get something working from beginning to end, and then I can come back and I can change the C2 method or add new ones. So then I dropped in a library called Request. It's like a high level HTTP library, and it's super full featured. Like this is a large and complex library. It's built on top of like the full async framework. So it's pulling all of that in, but it let me just, okay, cool. I got connections back to my server and I'm getting orders. Now I can start implementing other features. Where if I was in C, yeah, I'd still be screwing around in C land. Like it'd be a little bit better because I'd be working against curl and not, doing this low level ICMP stuff, but it's still slow going. Like that's not fast development there. And that is one of the easier to use C libraries and more mature. So it's really nice to be able to have that like work really fast and then come back, clean up and optimize. Yeah, cross compiling. So uh, it's I have had I've had to work a lot in weird architectures in the past, and I've sometimes struggled a lot with getting cross compilers for this like weird architecture and OS together. And like I have memories of this system I worked on a long time ago. It was like a MMU-less. MMU is the memory management unit. Linux system on ARM. And because of that lack of an MMU, most normal ARM compilers, most features in Linux don't work properly. Uh, a lot of like higher level stuff, like we got really excited, we got Perl running kind of once. Like it crashed if you did like certain things, but like we're like, yeah, now we're cooking with gas. But like I remember a lot trying to update our compilers and fighting with that, building it for this weird system. With Rust, it's not too bad. Rust supports a lot of targets and it supports them fairly well. There's usually not a lot of work that you need to do to get it working. So for this initial version of the implant, my CI system, I'm building for OS X, I'm building for Windows 7 and above, uh, x86, Linux, and ARM I don't remember which version of ARM, but a 32-bit ARM. And they're all generally pretty easy to build for. So this shows some of the commands that I have to do. Like, it's kind of gross, but it's in the scheme of things of what cross-compiling can be, it's not too bad. So I just do an apt-get install to be able to get some of the tooling that I need. I have to tell Cargo, this is one of the steps that's really confusing to me. Cargo is the build tool for Rust. And I have to tell it, hey, if you're building for ARM, use an ARM linker. I don't fully understand why it can't figure that out itself. It's like, hey, building for ARM, maybe I should use the ARM linker, but you have to tell it that. And the next step, you just have to download the backend for it. So you add a target, and then that's it. You can start building for ARM. So it's pretty easy and straightforward. Does anybody have any questions on any of that? Cool. So I will say one of the, while I'm saying that the story of cross-compiling on Rust is pretty good, but it's not great. So one of the things that's unique about implants or malware is you're generally targeting really old unpatched systems, because like that's what gets exploited. And so when you're writing like commercial software, you can reasonably expect like, hey, this is going to be software released in the last 10 years, and you can get away with that. But you really can't with implants. At work, we often target things. There's a joke that we target systems that are old enough to buy smokes. Someone else there has done a really good talk on that if y'all want to check it out. But so like Linux 2.4, Solaris 9, Windows XP, these are things that are often in our crosshair, and this is a bare minimum requirement. So Rust makes it a little bit harder. So like I said, I'm building for Windows 7 and up right now, which isn't too bad. And Rust has the ability to target XP, but the compiling process isn't straightforward for it. The oldest Linux it supports is Linux 2.6.38, which, that came out 8 or 9 years ago, but it's still pretty modern in the scheme of things of what we're going to be targeting. But one of the other nice things, but C handles that well. You can, whatever ancient decrepit system you want to find that someone's found in a dumpster that they want to drop an implant on, you can probably find a C compiler for it. So that is one major downside that Rust has. But yeah, generally newer systems supported really well. Tons of OSs, ones that I've never even heard of, Rust will support. They've got a pretty good tiered system too. So there's your tier 1 systems like your Linux x86, OS X, modern Windows. They guarantee this is going to work. You're not going to see any regressions. Your compiler is going to run on these systems. And then it's going to start running down to, they have a tier 2, 3, there might be a 4. The farther you get down, the more likely you are to see regressions. But they're still generally pretty good about if this support gets mainlined, like it's going to stay, and they do a pretty good job of keeping those together. But if you get to the point, and I've talked to a few people who do this, where you've got a target, you really need to hit this. Like someone's got like a VxWorks. Actually, VxWorks is supported, so that's not a good example. But someone has some just crazy old architecture or very, very old, out-of-date OS, and we absolutely have to build for it. Rust supports a not impossible process of custom build targets. At our local Rust user group, someone built a backend to target the N64 in Rust, and he actually wrote a PowerPoint clone in Rust to run on the N64, and he gave his presentation with that, like clicking through with the controller. It was pretty cool. And I've got another friend who works in the embedded space where he's had to do it. Did not sound like he had fun, but it is approachable by mortals. So next, why not Rust? So while I'm a huge fan of Rust and I just love writing things in Rust, I also like getting things done and getting things done properly. Rust isn't always going to be the right tool for everybody and for every job. And there's a few things that Rust has going against it here. So one of them is file size. I've never been one to really care that much about what my executable size is, because normally I'm deploying this to big iron somewhere, or it's like on a modern computer where we have gigs and gigs. Like, who cares? These implants are often going to be targeting, once again, like I said, really out-of-date systems, or embedded systems are a great target. So, your IT staff is coming through and they're patching all the desktops and all your servers. But like, what about your like IoT enabled aquarium, or like your webcams, or someone put a tea kettle on the internet? These things are often running like popular open source code, and they're not getting patched because the manufacturers don't care to. They don't make money by patching product they've already sold. So this stuff is going to get older, it's going to get out of date, and there's going to be known public exploits for them. So people can exploit this tea kettle and land an implant on it. And so now they're going to have a good persistent place on your network. And, if you're talking about implanting a tea kettle, yeah, the file system size matters. Like, there might just be like a couple megs free in there. And so it's really important to get the executable size down. And also, another reason why it matters is sometimes your path into a network or onto the device that you're implanting is through some weird hurdle. Like, maybe the red teamers, the way they found onto the network is through some bug where they're only able to push like 5K at a time through it. Like, some poor handling in a web client, or maybe they have like a kind of shaky network connection set up somewhere because it's being routed in a weird way. So it's important you can't just drop a 20 meg file in. So with Rust, there's a lot of tricks you can do to keep the file size down and get it down. And you can, if you want and you really want to put out the effort, you can make an executable every bit as small as a C executable in Rust. But every step of the way, you're going to be turning off more features and more helpful things, like things that you came to Rust for to make your life easier. So like the whole standard library you can remove. You can remove some parts of the error handling to save size. So it's a back and forth. I'll go ahead and say my goal on this project was to have an executable size under 1 meg. It ended up weighing at about 1.6. So like, not too bad for something that's got a remote shell back and is doing it with some fairly heavyweight libraries. But yeah, that problem's there. Yeah, and so it's got a reputation as a very difficult language to learn, and I'll be honest, it's pretty well earned reputation. I personally think it's worth it, but it takes some time. At ThreadX, we usually talked about from the day someone was hired, it took about 6 months for them to get absolutely full speed. And so that's full speed where we can drop them into any part of the code base and they can deal with it. We had parts of the code base that you didn't have to learn more advanced topics. And so you could usually drop somebody in there pretty quickly, like on the first couple days, if they're a competent programmer, and they can cut their teeth in it, because they're not going to have to deal with some of the ownership and borrowing problems, just because of the nature of that part of the application. So that makes it really tough. And there's also just not a lot of Rust developers out there. So when we started recruiting a lot more, we looked for people who had Rust background. We really didn't find many. And they said, okay, my personal path into Rust was through Scala, and I found that it made it a lot easier to pick up, because some of the difficult concepts that exist in Scala, like the functional nature, being able to deal with like results and options, and like the way the macro system works, it's really similar in Rust. So I was like, I was talking to the recruiter, and I was like, if you need a larger pool, you can look at Scala developers. And he gave me this look of like, yeah, when your bigger pool is Scala developers, you're in trouble, because that's already a really small pool. What's kind of funny is when we were training people, like when we had interns, they generally didn't have as much trouble learning Rust. And some things that Rust does is really counter to things that you're used to in other languages and the way memory management is handled. But when you're an intern, you don't have those like notions. You haven't learned that stuff. You don't have to unlearn it. So they're just like, yeah, I don't know, this is what the computer wants. Like, these are the rules. And so they ended up picking them up pretty quick. And we had a couple interns who were they were pretty productive pretty quickly. So does anyone have any more questions about like downsides of Rust? I will try and be as honest as I can about what's good and what's bad about it. Cool. Okay. And that means I don't have to say anything else bad about it. It's perfect, except for those couple of things I mentioned. So I kind of want to give a quick tour of like really high level of some of the things that Rust brings, how this maps to languages you may already know. I actually should ask the crowd, like, what languages are most people here used to? I think this is a .NET heavy crowd, but I'm not sure.
Yeah, that's about right.
Okay, cool, awesome. I don't know much .NET, so I'll try my best. But
a lot of people here probably know JavaScript too, so if you want to compare it to that, that probably works.
Awesome, cool. So this is a simple hello world. I figured since the nature of what I'm building, it's hello from someone else's computer, would be a little bit more applicable. So one of the first things that I have that Rust has that I like is its trait system. So Rust has no concept of like an object oriented like inheritance hierarchy or anything like that. The only thing it has is traits. Traits, sorry about that. Traits behave a lot like, and I believe that this is the way interfaces work in C# now, where you can have a default implementation on a method in a interface, and someone correct me if I'm wrong, but you can't store state on a C# interface. Is that correct these days?
Correct.
Cool. Okay. I was going to say nobody said no, so that must mean I'm right. So it's going to behave the same way here. So it lets you define a contract and with some default behavior if you need to, but you're not going to be attaching any state in there. In the bottom example here, so we'll go through this. I have a trait, and this is the trait that I use in my actual code, where we've got a check-in, and I've got a state manager. We have a mutable reference, which I'm going to be diving into those in a little bit of what that means and what's going on there, and my logger. And then it's going to return back a result of either the reply from the server or an error And then the second one is I can say, hey, this trait here, it depends on this other trait. So if you implement C2 manager, that means you also have to implement C2 method. In this case, and I'll kind of dive into this in the architecture, I have a C2 manager, which handles all my different types of command and control you can do of like, okay, are we calling in over HTTP? Are we calling in over UDP? And it lets you switch through those. But like the requests that or the contract that manager gives to the rest of the application is exactly the same as the actual C2 implementation. I'm going to ask the manager, hey, go check in. And the manager is going to ask one of the C2 methods, hey, go check in. So I see a lot on the internet, people try and find some way to do like inheritance in Rust. And I've never seen it go well. Like it's usually like a few months of frustration, and people will pick that up if they're porting over like a really object-oriented heavy code base and they're trying to port it to Rust. So it's really best to just accept you can't do it, really get in the mindset of traits of this is how abstraction works, and this is how you add features into a data type. So anybody have any questions on traits? Cool. So pattern matching. A lot more of these examples I'm going to have I just pulled from the Rust book, which once again, another nice thing that I love about this language is MIT and Apache licensing is everywhere. It's kind of like the default for everything. Like the compiler is released in it. Almost all the libraries are Apache, MIT licensed. The book, like you can buy a hard copy. Actually, I have my hard copy right here. So they have that, but you can go online and they have all the source code that they use to produce the book, and that's all Apache and MIT licensed. So it's a really nice license to work with if you're working with something that's closed sourced, or you just want to kind of borrow something. You don't want to worry about the ramifications. So in this case, I just wanted to borrow stuff for a presentation. So pattern matching, this lets us match over, and this is something that I'm really used to in Scala, and it works identical in Rust. I don't know if C# matches as well, but we can match over an enum. So in this case, sum is our option enum, where or it's a member of the option enum. So option can be either sum or none. Sum has a value in it, none does not. So in this case, what we're doing is we're going to look at the value, and we can really succinctly, easily write, what would be a few different if cases of, if we have sum and the value inside it is exactly 50, then we're going to print this. If we have some value wrapped in there, n, and it is equal to y, then we want to do this. And then in this case, it's going to handle none, or if n equals any other value. So it gives you a nice succinct way to put all this information, and also each one of these can emit a value. So you can easily map one value to another using pattern matching. So I think it's a really nice, useful tool. It helps make logic generally pretty readable and compact. And one of the best things is if you're dealing with enums, it requires you to exhaustively match. So I'll show you that in my code base, where I have an enum of all of the different like C2 methods that I might receive from the C2 server. And I'm checking them in my main event loop. And the compiler says, hey, if you don't handle every single message and do something about it, then I'm not going to compile this. So the pattern matching has to be exhaustive. which is just another nice thing for quality. Making sure, oh yeah, oops, I forgot to handle the file download message or something like that. It's like, yeah, it's covered. Where, switch cases in some languages, you don't always get that. So macros I've got like really mixed feelings about, but they're super cool. I'm glad they're there. And like, I watch them like a hawk in code review and kind of hate them being added in code bases. So a macro lets you there's two types of macros in Rust, but they both let you produce more Rust code. So something that would be really copy and paste heavy, or something that you would normally reach to reflection for, you can now do in compile time, and have it checked by the compiler. Because like, I think we've all hit some like weird dumb bugs because of something we've done in reflection that was kind of hard to troubleshoot or reproduce. Being able to push that forward to compile time lets it be a lot faster and lets you reason about it a lot better. Um, Downside of it though is, as you can see from this code example, that's super gross and weird looking. And I'll walk through how this macro works and what it does in a moment. But it also makes your compiles pretty slow. So part of our code base that I worked in the past, and I've worked in a couple that were super macro heavy. And I particularly remember one, the compile time was about 30 minutes just because of so many macros producing so much code that wasn't always used and got stripped out at the end. And macro code is not as easy to debug and walk through. While I personally think it's easier to debug than reflection, just straight up Rust code is a lot easier to debug. So in this snippet, what we have here, and this is what we call a macro 1.1, is we have some repeating expression, and then we will have this line, and then for each expression that's repeated there, we will make temp_vac.push, and then that expression, and then it will return temp_vac at the end. So what this lets us do is, this is the actual invocation. You can say vector 1, 2, 3, and then it's going to produce the code. We'll have that line. We're going to push 1, we're going to push 2, we're going to push 3, and then we're going to return temp_vac into V. So it's kind of like a nice, easy copy and paste. And I think you might see where people can kind of get out of control with it. Like, I've seen like a wonky ORM built in this, and like a lot of different things. So it's nice. It's a powerful tool, but you definitely have to be careful with it. So that's one type of macro. The other is, which I really love, and they're a lot of fun, and these are the ones that map well to Scala's macro system, is what's called a procedural macro. And they're a little bit, the learning curve is a little steeper, but what you're able to do with them is basically unlimited. The procedural macro, when it is run, it is fed in an abstract syntax tree, basically the view of the compiler of the source code at that point. It is handed to the macro, which is normal Rust code, and that Rust code can manipulate that syntax tree however it wants and returns it. I'm not going to dive into them a lot. I don't have a lot of experience writing them. I wrote one for funsies. They're difficult, but I am going to show you where I use them a lot. There's a lot of really, really great ones that have been built by other people that are out there in the ecosystem for serialization, to get around silly little wastes of time. And these are like really well vetted, easy to use. Another one that I'll go into is, there's a great one for validating data inputs. and you can just drop that in and it's going to generate all your boilerplate code. And you just have to call validate, and it's going to make sure that it's good. So it has functional concepts. It's not a super functional heavy language. People on the internet have strong opinions. I could end that with a period right there and just say people on the internet have strong opinions. But like on this one in particular, on if Rust is a functional language or not, kind of not going to cover that. It's just those concepts are there. You can do, chaining, stuff like that. So ownership. This is a big one, and it's going to take a little bit to explain. So the concept of ownership is the way that Rust works without garbage collection and without manual memory management. So normally in C and C++, you allocate something and later you free it, and you are doing that and you have to keep track of it. And in a garbage collected language, it's going to track and say, okay, something that's been allocated, we've called new, that exists. It's going to track, hey, am I able to reach this value from root anymore? Like, are we able to get this, or has this, have we lost all references to it? Is it time to free? And then garbage collection will come through, sweep. Okay, there's no path to it. We're going to free that. That background process, that provides overhead that's sometimes unacceptable for certain applications, like real-time processing of sound, something that's maybe you don't own the memory. So like I'd mentioned earlier, we had that module that fit inside Nginx. We didn't always own that memory, so we couldn't have garbage collection. Could be like, oh nope, free that, and it's like it's actually Nginx's memory. So C developers often will talk about ownership, not in the concept that in the way that Rust developers talk about it, but in like the architecture of the system. Like I will say, oh, the inventory module will own this data, or my config parser owns this data. And that means that it's the config parser's responsibility to free it. So it will allocate it, whatever else will use it, and it will come back and it will free it. Or the config parser will allocate it, and then it will pass ownership off to something else. Something else owns it now. It's their job. When they're done, they need to free it. So all Rust did is took this like architectural concept that like C developers have been talking about for decades, and they make it part of the language, where any bit of data that you have is owned, and any other parts of the system, they can either take that ownership away or they can just borrow the data to use it. So in this case here, we have, so before I get into that, does anybody have any questions about that kind of a higher level, like of the C world and that terminology? Cool, awesome. So in this place, or in this example, we have string. At this point here, we are allocating a string that says hello, and that is stored in S. And then here, I can take a reference to S. So that means I'm not taking ownership. Like in the example where I was talking about before of one module is going to own it and then free it, but someone else wants to look at it, they can view it, and it's going to come back to me. When I'm done, I'm the one who frees it. So in this case, S owns the string. R1 is going to borrow the string. It will look at it. When it's done, that's it. Nothing's going to happen. We're not going to free it because S still owns it. So R1 has a reference to it. R2 can take a reference to it. You can have as many as you want taking immutable references or immutable views into it, because that's totally safe. Everyone can look at it. But once someone wants to write to it, that's the problem. So in this case, so this code won't build because R3 wants to say, hey, I want a reference to S, but I want to be able to write to it. And so then that's going to start invalidating assumptions that R1 and R2 have. This data is not going to change underneath them. So you cannot take, like, if you're taking a mutable reference to something, that's exclusive. You're the only one who can have a view on it. You're the only one who can work with it. And then once you're done, you can drop that reference, and other people can then take immutable ones or mutable, whatever they want. And so then finally, now we get to this point where S drops out of scope. And so at that point, the compiler says, cool, no one's borrowing this because these have been freed. And so now we can free this too. And then everything's cleaned up, and we know exactly at compile time, when is this getting cleaned up? Who's getting cleaned up? Whose responsibility is it? And this is all demanded and described by the type system. And so that's the big thing that lets Rust be a lot safer. One of the big things, a lot safer than C, and it lets it avoid, double freeze, use after free, and things like that. So when I say, does this make sense? I don't expect it to make sense. I honestly was writing Rust professionally for a couple months. Like people were paying me, and I was like, I still don't get, like, there's some compiler magic, and I kind of have a gist of when the compiler is angry at me and when it isn't. But does that make sense to everybody?
At least in the simple example, it makes sense.
Awesome. Cool.
I do have a question from Brent.
Yeah.
Have you worked with data structures beyond trees, like acyclic graphs or cyclic graphs? If so, do you have tips on representing those in Rust?
No. Okay, that is such a great question. And that is, if it's the Brent that I think it is, I know he has Rust experience. Otherwise, it's like, yeah, that person definitely has Rust experience. It's an interesting, like, very painful problem in the Rust world of, like, I think we all remember our, like, sophomore year of like undergrad CS, and you have to, like, write, like, a linked list. And it's like, that's something you do then. It is super, super hard to do those in Rust because of these ownership constraints. There's a lot that's going to go into making, like, acyclical graphs or data where they're both going to be referencing each other. It starts getting really difficult. I have thankfully not done it, and I have only used other people's that exist out there online. Cool. Any others? Awesome. So one other thing that is shown here, and I just want to call out, is Rust is immutable by default, which is another, it warms my heart because it makes the code base a lot easier to work with. So unless that MUT keyword's there, you can't change that data, and you have to opt into it. That also gives the compiler a lot of power because it knows exactly when things are going to get changed and when they are, or when the program has the ability to change things. So it unlocks, like, new classes of optimizations that it can do. And it's part of the reason why Rust can be so fast. So cool. Send and sync. This is another, like, weird thing that Rust does that I have not seen in any other languages before. But I love it now that I'm used to it, and I think it's really powerful. So I talked before about traits. Send and sync are two traits that the compiler can assign to, can and will assign to data if it decides that it meets those requirements. So send says this value can move between threads. And sync says this value can be viewed between two different threads. And so pausing, getting my thoughts, because it's an interesting and simple project or concept that has a ton of ramifications in your code base. So the way the compiler decides if something is send or sync is if all members of it are send or sync. So we're going to look at just send right now. Or I'm sorry, just sync. That's what my example is. So in this example, I have a trait that's called confirm sync. And I'm going to say, hey, if you can implement confirm sync, I require that you also implement sync. This is just a shorthand way to say, hey, I just want the compiler to bail out if something's sync or not. Normally in a larger code base, you're going to see this blow up in less succinct ways, and this error show up, like because you're actually trying to use something in a sync way if it's not sync. But so all of the primitives in Rust implement sync. All the primitive data types. Things that aren't going to implement sync are going to be things that are like tied to OS resources. So like an example is like args that you have parsed in from the command line. These are not sync. They rely on some kind of OS resource that it's like, we don't know if we can pass this between or reference this between threads. But in this case, U32, so unsigned 32-bit integer, that's sync. Therefore, that means IAMSync is sync. So I can implement that, and that's not going to break. In this other example, I have something IAMNotSync, where it is a cell of U32. So cell is a way to make something mutable. It's like a hammer you can hit something with to be like, yeah, this thing, we can start grabbing mutable references to it if we want, even if it's part of a immutable data structure. And because cell is mutable and might be changed, we can't safely share this across threads. So that is not sync. So in this case, if a structure contains a cell, which is not sync, therefore the structure is not sync. So, okay, cool, this makes sense. Who cares? Why? Like, why is this valuable? So now we're gonna like zoom out to like a 10,000 foot view of where this is going to show up in your applications. So like, let's say you have a thread pool manager that you're going to, all of your web servers workers are going to be sharing. It's all these different threads. They're going to be reaching in there and grabbing stuff. It has to be sync. It needs to be. And so that means that the compiler is going to have to say like, okay, cool, I trust this. This can be shared. And so you're going to have to do something to make it sync, which is apply mutexes in the correct places. And so this is what allows Rust to be able to chase down data race issues, is to be able to communicate, hey, the developer has done the work needed to do to be able to make this safe to share against across threads. This is a mutable piece of data, like a thread pool, or in this case, a mutable 32-bit integer. They've wrapped it in a mutex, which now makes it sync. And so then this can be shared in the application. I think a lot of us have been through the pain of having a single threaded application and be like, oh, we just need to make this multi-threaded for like whatever reason, like to do uploads of payment processing in the back end, or like, in the background, or like checking for updates or something. And the race conditions that you run into, this is a control that Rust adds in to find those, of saying, hey, the developer hasn't done what they needed to do to make sure that this is safe. So don't allow them to build it, don't ship it. They need to fix their problems. Does that make sense? Cool. Cool. Everyone's an expert so far. No questions at all. I love it. So I'm not going to dive in too much on what send is. Send follows the exact same rules. It just means you can send it across. Stuff like file descriptors are things that aren't send. So now we're into unsafe. This is the big hammer. This lets you do whatever you want. Rust has all these safety controls in it of like, I was just talking about send and sync. If I'm like, no, I know this is sync, compiler, I don't care. You can put unsafe brackets around it and just force it to be sync. And it's like, yeah, whatever, deal with it. Like this is right. You need to be really careful with it because it turns off all your safety controls, but it makes it where you can do whatever you would normally do in C. So this example here, it's just calling a external C function, the absolute value. So it's, pluck something from the C standard library, and you can call that. It also, you can start referencing like a slice without kind of bounds checking. You can pull a pointer and start doing pointer arithmetic, addressing like, if you're writing a device driver and you need to write directly to a certain space in memory, because that's like a register. Yeah, just right to that place in memory. It's fine. All safety controls are off. In the wider Rust ecosystem, this is a really controversial tool because there's a lot of performance improvements that you can unlock by using unsafe. And a lot of Rust developers don't use unsafe. And you'll see a lot of crates where they'll actually put in a compiler flag saying forbid unsafe, like no unsafe in this crate. And people will sometimes, Redditors will get real grumpy if they think that you're being a little cavalier about unsafe. And that there's been controversies in the Rust community about that, about either people thinking they're, this certain library is way too cavalier and there's unsafe everywhere, or people are being too picky and like this is okay and this improves the performance and the flexibility of a library. So definitely a controversial thing, but it's important that it's there and that like often you just need it. Like I've used it a fair amount. Anything FFI, like you're calling another function, like I'm parsing input from C, that's all unsafe and you need to do it. But this is the other nice thing. It gives you a small bit of audit space. So like, or space to audit. So like if you have a large C code base and something goes wrong and you start getting segmentation faults, it's like, I don't know what's causing it. Like anywhere, like everything's unsafe. It's all garbage. But with Rust, you're able to start on these. Like these are the most suspect places that could be causing a segmentation fault. You can audit those, work from there, and work out. Chances are the problem started there. It may be exercised elsewhere, but still, it's a great place to start your audit. Cool. So that is a quick tour of like really quick of Rust. Does anybody have any questions about, does it have feature X? Does it have feature Y? Like, why does it have this? Anything like that? Awesome. Cool. So I'm going to talk a little bit about my implant and what I did here. I'm going to pull my notes up so I get away from just a screed and get to like I had some points that I wanted to cover. So my implant, I started out, as I'd mentioned before, I wanted to do ICMP, C2. It was taking too long, so I was like, I'm just going to do HTTP. I'm going to come in and replace it later. My goal, keep the file size relatively small. Like I said, it's 1.6. It's respectable. It's chunky. It needs to go on a diet. Ultimately, I just want to be able to drop this on a device, and it's going to have credentials baked in and information to get back to my C2 server and then I can give it orders where I have a remote shell. I've got some file manipulation stuff that I'll be adding soon. And I also have a way to remotely edit the config on it. And you're going to see in the demo, like, why would we want to edit these configs? What do we want to do at runtime? So I'm just going to drop into some code. So how am I doing on time too? Cool, I got 30 minutes, so I will make it quick, and we won't get too much into the nitty gritty of a lot of stuff, but I'll show you some of the stuff at the high level. So I'm a huge fan of CLion. It's a JetBrains tool, mostly made for C, but it has built-in debugging functionality for Rust, and it just like works great. It annotates all your types and everything, and it honestly just makes this a much easier language to work in. Other people have tools that they like. That treat them well. There is a backend called Rust Analyzer. It can plug into most anything you want, like VS Code or whatever, for like tab completion and everything. So one of the things that you may have heard about Rust is the compile times are just like absolutely atrocious. I actually mentioned earlier some slow code bases I've worked in. One of the ways to help with that is a workspace. It lets you put multiple libraries all inside one workspace, and it's going to be compile their dependencies together and resolve them together. So there's going to be less duplication of like rebuilding these external dependencies. One of the reasons why builds are so slow is if you've got external dependencies, it's pulling the source down. And on every clean, it's building all these third-party dependencies from scratch, which it takes a while. And like you also end up, for most decent-sized projects, you have like 8 different versions of like MIO in there, just because people don't stick to the same one very well. So it's the way we define our dependencies is just a TOML file. Super easy to do. And this is something else versus C, like, C# and a lot of other languages have really great package management tools, and they have for a while. C's never really had a great one. Like there's been some starts and stops on ones, but I've never really liked any of them. It's really nice just to be able to drop in. It's like, yeah, this works great. This is enjoyable. So you just call out your dependency and the version. You do have the ability, and I use this quite a bit because once again, we're trying to keep file size down. You have features that any library can expose that you can either turn on or off, of like, hey, I don't need all this other stuff in here. Or, in one of the libraries that I maintain online, I provide a feature to turn on, it's for cache, and you can turn on or off like the hit miss ratio in there and tracking of that, because most people don't want to pay the performance overhead because they don't care. Like they just want it to cache it, but some people want that because they'll use it in their monitoring. So in this case, for that HTTP library, I tell it just turn off everything. I'm going to opt into what I want. I want it to be blocking. I don't want to use the async version of it. And I want the JSON parsing built in. And I say this is optional because I've made it where just like these other libraries can compile things in and out, I can do the same thing. So like as I add more C2 methods, I can add them in. I can keep the old ones in there, and I can compile in and out anything that I want by declaring these in my features. And this is just a really nice way to do conditional compiles. So to keep file size down, I'm able to call, the optimization level, optimize for size, turn on LTO, so that's link time optimization. in C world, you have all these compilation units, and then you link them all together, and then you have your executable, and you can tell your compiler, hey, do another pass over that, and I want to compile after the link is done, to trim it down more, because sometimes there are optimizations that exist across compilation units, and we're going to have the same thing here in Rust. A compilation unit, not to get too into the weeds, is like the scope that a compiler is going to be looking at. In C, it's per file. In Rust, it's per library. So I'm going to skip over codegen units. It's not important. Nobody cares. So panic action. So you can panic in Rust, and it behaves just like an exception. You cannot express any information that's useful in a panic, and it's generally frowned upon to catch panics. Typically, if you're panicking, it's like exit the application, get out. There's a lot of stuff that the compiler packs in there, so you can grab an exception, you can handle it. You get like a pretty stack trace. I don't want a pretty stack trace. Like if an IR team's looking at it, I don't want them to see that. So I just have it abort, save some file size, and yeah. And then finally, you can also call out. So while this is a nice thing, and Cargo provides a lot of tools that covers like 90% of projects of what you're going to want to do, often there's always something weird that you want to jam into your build script somewhere. And Cargo lets you do that by having a build.rs file. For me, what I want to do is I want to be able to take in a TOML file, which is going to define, all this stuff that I mentioned about that other implant bakes in as a step after compilation. I'm just baking it in during compilation. And so I have that as part of my build RS. I just generate a file with everything I need. I found a crate online that does it. And yeah, I'm not going to lie, this was lazy. I don't like it. I really think that I should move instead to a post-compilation baking step where it goes in and it manipulates the executable. The problem that this introduces is this. So if our attack team wants to use this, they need access to the source code, and they're going to have to do like a fresh compile every time that they're wanting to deploy this on a customer network, which that's not going to work. So yeah, you're going to see often in this code base, you can call out, this is just a conditional compile like anything else, where I can say, hey, if debug assertions are turned on, turn on these extra features that are helpful for me. And so this one's a logger. I don't want this stuff built into my final build. I don't want someone to be able to take apart my application and see these log statements, or I don't want this stuff diving into the build. So on a release build, that's all just knocked out. And by the way, we will not be walking through the whole thing because that's a lot to do. And oh no, my go-to definition broke just as I'm talking about like how much I love this tool. Oh, I know why. It's one of the downsides of workspaces that I want to call out is if you do weird compiler flags, or any compiler flags have to be applied to the whole workspace. They can't just be applied to one library inside it. So that means that my implant itself is actually not as part of the workspace, and so it breaks the IDE. So we'll drop into the entry point. I just want to give an example of like, this is a real world place where I'm using a macro. Is one thing that's useful that macros can do is give you variable amounts of arguments. And so all I'm doing here is I say if someone calls debug panic, I want to take all of these arguments, I don't know how many they're going to be, and pass them into panic if this is a debug build. So I have this built in, and this is a consistent thing with implants, is you want them to be resilient as possible. If something breaks, I want them to keep trying. I want them to like try another C2 method, try a different, like if we have a second address baked in, try that, wait a while, try later. But when I'm developing, I don't want it to go through that. If I see something go wrong, I just want it to bail out right then and there. So then I can go fix the problem. So debug panic is a command that I say, okay, if I'm developing, bail out, tell me about it. I'm going to go fix that bug. But if we're in production, try and recover, try and figure it out, try and do better. So at my startup, what I'm going to do is I create a couple different things. I have a remote logging manager, because another important thing is when this is out in the field, like I don't get to touch it. I don't know what's going on with it. I want it to be moderately chatty to me, or if it's in trouble, like let me know. So I've got a remote logger that throughout the application, anywhere something's going on, and it's got variable log levels, just like a normal like log4j or something like that. So I can log it error, warn, info, debug. And so that's passed around. And then on the next check-in on the C2, I'm going to push up a portion of those logs. So that's what we're setting up there. And then our state manager, this handles anything about configs, what C2 methods have failed, what C2 servers have failed, so we can move down the list. So if our first one failed, we're going to mark that. We're going to try the second one. That worked. We're going to stick on the second one for a while. Something else it does is, if you'll remember back in the beginning of the presentation, I was talking about the GRU implant, and they generate the unique ID to identify themselves through the login process. I just do that at startup because that login process, from what I was looking at, it didn't bring a ton of value. So I'm going to generate a unique identifier for, I have one for the build that's generated at compile time. And there's just a crate, you can pull it on offline that'll generate it for you. And then I generate a random UUID too. And I store that in there. Just so I know, so let's say I've got something, it's out on some network somewhere, and I see the same build ID, it keeps checking in, but we're seeing different, I call it an instance ID checking in. Like I'll see an initial check-in, it's got an instance ID, never hear from that instance ID again. And then I hear, bam, another C2 connection coming in. It's the same build ID, same IP, but it's a new instance ID. What that tells me is my implant's crashing. Something's killing it. I don't know what. It's able to start itself again and report back, but I don't know why it's crashing. So it's a really useful identifier of something being wrong. And I actually started using that in a past project that wasn't malware. It was customer deployed equipment that it made it really easy to like smell problems and identify them quickly. So go back to our entry point. So we've created that. We're going to set up the C2 manager, which once again, this just manages our C2 endpoints. It's going to handle these check-ins for us. And we're going to drop into, there's just a boring old event loop. It's just a while true and with a sleep at the end. So in this, we're going to ask the C2 manager, hey, do a check-in for me. C2 manager is going to pick a C2 method, phone in. Eventually, it's going to do its damnedest to get a connection somehow, however it's going to do it. And if we get one back and we get a response, in that response, we're going to have a list of instructions, and we're going to get a new optionally a new check-in time. And so in this case, I'm going to walk through. We're first going to take a look at our instructions. And this is something I mentioned earlier on the pattern matching. So I'm going to pull out my instructions, and I want to match over them. And I want to say, hey, I've got an instruction here. I want to compare it against all my instruction types. As a developer, if I forget, like if I leave out like the update config one, builds will just stop working. So I actually have messages that are mostly implemented. They're on the C2 side. I just haven't finished them on the implant side. And they hit this unimplemented macro, which just says bail out with this error message. So in this command, or in this case, we got two that we really care about and that are really useful, is run a shell command and update config. Update config will let us change C2 methods. It's going to let us change the call-in interval. So the C2 is happening, in this main action loop. We're cycling through this some interval, like once a minute. Maybe we're going to phone home. This lets us say, hey, I don't think I'm going to use you for a while, and I don't want you to get caught. Check in once a month. Or it's like, hey, I'm ready to cause some trouble. I want you to check in every second, so I have like quick responsiveness and I can get the job done. So you're able to change that through this configuration, or on a check-in. I can give you a temporary, like, hey, I want you to do this one command and then like phone back home immediately, because I'm going to have another command for you once you're ready. So I'm not going to dive into the implementation because a lot of it's not super interesting. It's going to look a lot like you're going to implement it in any other language. So one of the things yeah.
It's a good time. What are you using for CERD or CERDA?
Yes, so I am using JSON, which is I'm going to give some context on that. CERD is that actually leads in perfectly to the next section. So I'm gonna we're gonna go to where everything's defined. CERD is a really powerful macro-based serialization and deserialization library. So you can define your data structures and you can tag them, hey, I want this to be serializable or deserializable. And it's going to generate all the machinery for that that's needed. And then whatever kind of serialization library you want to use JSON, you want to dump this to a TOML, like, does not matter. The CERD backend's always the same. And then you can hand that off there and it's going to generate it. So you say that it's like, what is the serialization that I'm using? So right now it's JSON. I want to switch over for low effort. There's a really great implementation of message pack that's pretty small. It's really fast. The on the wire, it's small, and on the executable, it's really small. It's like message pack is just really nice to work with. I didn't use that because I don't plan on sticking with HTTP for long. So I was just like, yeah, JSON, whatever that's built in. Like, I'll mess with this stuff later. And so now I'm going to show you, and that is a perfect segue into the next thing. So this is something I love that Rust does, is if I'm doing a client-server relationship like this, often I'll have a protocol library that defines what all these structures are going to look like, what's contained in them, and then I can share that between the server and the client, and I don't have to mess with, there's a lot of other really good tools that are higher overhead to do this, like OpenAPI, but like this is going to fit in real small. It's going to fit in with my type checking and it makes sure everything's right. you do have to be careful with just like any published API. It's easy to make backwards incompatible changes to it. But yeah, so this is just a shared um, folder or shared library between my C2 and my implant. And I'm going to call out a few different things that are going on in here and the significance of them. So these triple whacks are a doc string. And so when I go to build our documentation, it's going to have that populated into the HTML, and it's going to look nice and pretty for like the high level of like a structure, or this is a new configuration, and for each member of it. Debug lets me build in more kind of like nice, pretty print stuff. Deserialize lets me deserialize it. Serialize lets me serialize it. Sometimes you want to do one without the other. And here, this is a library I love. I love. It makes writing like Rust APIs pretty easy. It's called validate. It implements, so if you call this, it's going to call a macro and it's going to generate a bunch of validation stuff for whatever that structure is. And you can define like, hey, I want to make sure that this looks like a phone number, or this looks like an email, or this string is no longer than 50 characters or something like that. And you get to define this declaratively when you're creating your structure. And then on your API endpoints, all you have to do is just call validate, and it's going to check everything for you and give you a thumbs up, thumbs down. Saves you a lot of boilerplate. And I'm going to show later the compiler is going to force you to always call validate. So, so going through here, everything in here is documented, because once again, another really cool check that Rust provides you is you can add deny missing docs. And so if someone's in here changing things and they don't document their changes, it won't build. I actually got a really great tip on Twitter a couple nights ago, is to set this to warn, and then in your CI, fail anything that builds with warnings. And so then you get the best of both worlds. You get to work quickly, do whatever you want to do, but then if it gets, before it gets merged, it's going to make sure that those docs are in place. But yeah, I really love having that there, and it makes life nice and easy to have a well-documented, easy-to-use code base. So does anyone else have any questions on what this protocol looks like and kind of this in general? Cool. So one more thing about this is these messages are going to be consistent, whatever my C2 method is. Like I may serialize this, like, you know, if we're using something that's limited on space, we may serialize and split it up across multiple messages. Might not, but so I'm going to jump really quickly into the C2 server side. So there's a lot of web frameworks that are available in Rust, and there's a lot of strong opinions on which one's best, worst, whatever. I don't really have super strong opinions on that. Actix is kind of the big one right now. It started out as an actor model implementation, and a really nice web framework grew on top of it. Some people have really strong opinions against it. I've used it in production. I really like it. In this case, I'm not using it. I'm using a framework called Warp. It's a little bit newer, and it's definitely shows that it is experimental in some cases, but it adds some cool features. And the thing that I like about it and what I wanted from it and why I picked it is Rust has full async await, similar to a lot of other languages that have it. It supports that, and it lets me do easy dependency injection. A lot of the other nice, fancy async await libraries, they'll do something tricky in the type system that will break doing dependency injection via traits. So that kind of crosses off my list. I think unit testing is crucial, and having like a separate trait to separate a data like access layer is like just crucial, bare minimum. I gotta have it. So, but one of the things it does is it has a router system that I've never seen before, and it's really cool. It's built off of um, what they call filters, and you can chain these filters together. You say, okay, if the URL is this, and if it's a GET, and if it has this header, then do this. So you're going to define it in your code, and this may be a normal thing in other languages, but it was a new one to me, and I am not, to be completely honest, I am not using it to its full ability too. So we're going to dive in really quick on what it looks like and why I've been able to do some kind of cool stuff with this router. So like I'd mentioned, it pops in with the type annotations here. So Rust does a lot of type inference locally. Sometimes that can be hard to use. And you're just like, oh, I thought I had a U32, but I have like an iterator. And the IDE will just show you, and it lets you know exactly what you have and gives you a good idea of what went wrong. So that helps me work pretty quickly. So I'm just going to pick the login endpoint. So this is where a human operator is going to come in with a username and password. They're going to log into the C2 server, get a JOT back to start doing actions. So we're going to look, does it meet these requirements for this path? Is it a post? Can we extract a body from the post, and does it validate correctly? And then it's going to include our data access object and our configuration so we can build a JOT. So having that there, it lets me say for any type of T, I have a generic, I want it to be send, I want it to be sync. It has to be deserialized owned, which is related to the serialization that I showed you earlier. And it has to implement validate. Go through, extract it with a certain size, pull it out, validate it, and if it doesn't validate, we're going to reject it, so it won't even route to the handler. So I know when I'm working with a handler inside this, at that point, this has already been validated. I don't have to call validate. I know things are good at that point. And I'm able to do the same thing with my admin APIs. We're going to have a filter that's going to require you to pull a claim out. And so we're going to look for the header. We're going to parse the JOT. We're going to decrypt it. We're going to make sure that it's not expired. And if it is, we're going to reject it. And then that gets included, that claim starts to get included in the signature of the handler. So if I see that there and I see there's a claim available, or if I see that there is a body of a post there, I know it's been validated, or I know that claim's been validated, so I don't have to worry about it. It makes the code easier to audit on code reviews, because you know people have got that stuff. So I think that is probably all that I'm going to dive into on the actual code. Because there's a couple more things I want to show, and I don't want to keep everyone way too late. So I use a tool called Docker Compose, which I love. It is a way where you can define what a system should look like. Multiple services connected, what talks to what, and we'll start them up. It will network everything together. And so then you have a really quick, easy to use QA environment. So in this case, all I have is a Postgres database, a C2 server, and an implanted system. And they're going to connect up. And then also my source code for every one of these projects is mounted in to the Docker container as a Docker volume, and it's watched. So if I edit the code, it's going to automatically reload my service, recompile everything, and I can just keep working, and everything's going to be working just fine. Does that make sense? Is anyone interested in the Docker Compose stuff? Because I'm like super excited about it. If not, cool. I will dive in.
It might be
go
worth,
ahead.
yeah, it might be worth looking at. I'm trying to think if I think we've talked about Docker here once before. I know some of us have used it some. So
cool. Okay, so Docker Compose is going to be a wrapper on top of Docker to define these networks in this like higher level view of the world. And so each service is going to be encapsulated inside a Docker image, and it's going to have its whole environment in there and defined in there. And so this is another nice thing, is that means I don't even need the Rust compiler on my local system, because it's going to be contained in that Docker container. So you can drop this new environment. You don't have to fight a bunch of freaking dependencies to make everything work. You just call Docker up. Your dependencies are going to be in those images and set up. So you have a TOML where you're going to be defining the services. You're going to find how you want it to build. This one's and then volume, that says the folder that we're running in on the host, map that into the Docker container in /app. So if I edit it on the host, my changes appear in the container. If I edit it in the container, the changes appear on my host. And so it makes a really seamless, easy to use development environment. And yeah, I say that my C2 server depends on Postgres. So I want to make sure that Postgres is up before C2 starts. And my implant depends on C2. And then that's about it. It connects all that together. I recently found this pattern, and it's just so great, because now I've got a working environment and I can start running tests against it. So I'm a strong believer of, like, as you introduce APIs, you should introduce tests for them. So like every API endpoint I have, I start adding, so on the C2 or the C2 admin side, so like where a human's going to interact with this, I just go ahead and write a Python script really quick of just, I'm a big fan of MyPy for type checking. It helps keep my code quality a little higher. So it's like login, give me the API. So that's like where this is located, a username, a password, and I'm going to give you a JOT token, or I'm going to throw an exception. So it's just like, it's really cheap, easy to do. As you add an API endpoint, just add this snippet. So then once I get everything all together and I have, something built and I have all these little scripts, then I can just make a smoke test really quick of, I want this thing to go log in, get a list of the implants, grab one, give it a command, wait for that command to execute, and then look to see if we got the response that we thought back. So I'm going to show that one working real quick, and then I'm going to show actually using this implant as a human would use it. Pipm, this is just to like get all my dependencies together. That's just a tool I use. It's super nice. It's another thing that I just recently learned. So it's called smoketest.py. This is going to walk through what I was just talking about. And one of the things that I want to call out is, so everything that's running right now, these are debug builds. And this is like every new Rust developer hits their head against the wall on this, is Rust debug builds are super, 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 super slow. Like you're like, why is this so slow? Specifically, the library I use for password hashing is wicked slow on a debug build, but exactly what you would expect on a production build. So cool. That just logged in. exercised some activity, made sure that it looked right. So, so now we're actually going to connect to this like an admin would. So I use a tool called CMD2. It makes it really easy to make these interactive shells that are just wrappers on a bunch of APIs. So set API in here. This just tells me, hey, where's the C2 server I want to talk to? I set that up. That shows up my prompt. I know I'm talking to this one. So like, let's say I'm a bad dude and I'm breaking into multiple places at once. It's like, hey, connect to the C2 server that's connected to the bank, or like connect to the one that manages the implants and the government thing, whatever. It reminds me this is who I'm working with right now. So I'm going to log in. My Docker Compose file calls out in the environment a default username and password. So when the C2 server comes up, if it sees that there's no users initialized, it's going to look in the environment and grab that username and password and create an account. So that's how that got in there. It's not actually hard coded into the code because that's a bad practice, but that's how they got initialized. So we're going to sit here, like I said, come on, hurry up, password hashing. So we're logged in. So I want to list my implants. So I've got multiple implants right now. That's usually a sign that I have shut this down and started it back up without nuking the database. So I'm going to cheat a little bit. The right way you should do this is have a last check-in time here, so you know, like, hey, what's valid, what's not. So this is the guy I want to connect to. So I want to get a remote shell, and then I give it the ID of the remote shell. So before I kick this off, I want to describe what it's going to do. I'm going to say, hey, it's time to connect. Let's get everything going. It's going to queue up a few different items of work for the implant. The first one says, when the implant checks in the next time, tell it to change its check-in period. So it's constantly checking in, because I don't want to sit here and wait every 5 minutes for like, when's the next check-in for my command? I want to run a command and get feedback immediately. So I do that. And so that's going to prompt me. So we're going to do run ls, and that's, so now that queues up the command in our C2. The implant phones home and says, okay, I want an instruction, pulls the instruction down, and it says, okay, it wanted me to run ls. I'm going to run ls. I'm going to capture the standard out, standard error, and the exit code of how this instruction ran. And then I'm going to phone that back home, and my shell is sitting there polling, waiting for this work to get registered back up, and then bam, it does. And so now I get this like nice live feeling. I feel like I have a shell, but we're working through this this like indirection, and then anything that's popping out to standard error is going to show up red. That makes it nice and easy to read. So a whole lot of to do for basically just getting a shitty SSH, but we can't just SSH to these servers, because often they're going to be behind firewalls. They're not going to be something we're going to route to directly. That's why we have to have them phone back out to us. So so one of the other things that I want to talk about too really quick, because I am over time already, is there's a lot of really, really great tools, like I'd mentioned, the static code analysis and quality checking stuff, that makes it really easy to build a really nice, solid CI pipeline for Rust. I've got one set up for this, but it takes 200 billable minutes every time I run it. because I'm actually doing builds and tests on Mac OS X, which is super expensive. And it's another sign of like how slow Rust builds are and actual impact. Like those 200 billable minutes, I have just been nuking my allocation for GitHub Actions like every month, and it's been an issue. So, so does anybody have any questions on that? Sweet. So what's next? I really just want to finish out the file manipulation, the port forwarding, being able to set this network so I can start, I can run port scans from my network, or I can from like the operator owned side and route that through this C2 mechanism and have it dump out into a compromised network. I really want to do the ICMP thing. It just sounds like a lot of fun. So that's really high on my list. And then I'd mentioned before, Rust has the ability to completely rip out the standard library. There's not a lot that I'm using on the implant side for the standard library. It's pretty crucial. Removing that and the HTTP library is going to save me, it's about 500K, which is like not an insignificant amount. So I want to get that down. What's most likely going to happen is I'm going to get bored and give up and like go do something else because there's a lot of new shiny stuff out there, and I might just post this all on the internet and open source it. So follow me on Twitter, and I'll post a link if and when I open source it. So ta-da, that's it.
Watch out if you open source it. People might put it in mission critical things and start giving you bug reports.
So that's yeah, that's even worse than it being used for evil. Like used for evil, cool, I'm not involved. Bug reports, it's like, man, I gotta get off my ass and fix that. Oh, that sucks. So and I didn't mention the whole reason why I did this is the initial reason is I wanted to try and convince my coworkers to take this on. I don't know if it's right to. So I think the right tool for the job really depends on like the team, the environment you're working with, the ecosystem. There's so many things, but the team's a huge one. We've got a lot of guys who know the languages they know really well. And like we're all able to write pretty high quality C, and this is going to be disruptive to a lot of people. So I'm not sure it's going to be the right answer, but I'm still going to, I still might try to get in there. So hopefully I'll get into some mission critical systems soon, aka our customers' networks.
Awesome. Well, thanks, Stu. If anybody has any questions, now would be about the last time to ask. Though I bet you can hit him up on Twitter. Well, thanks, Stu. We appreciate it. Next month we will have our meeting. I think we're going to do it on the 9th-ish, whatever that Wednesday is, because we don't want to do it right after, right around the 1st. So we'll do that. Michael Perry will be talking to us, I believe, about immutable architecture. We'll get that posted. So thanks again, Stu. If anybody has any questions, they can stick around for a minute. I'm sure he'll stick around for a sec. Feel free to unmute yourself if you want to talk.
Thank you, Stu. That's awesome. You made my night. Admittedly, my standards are lower lately.
Dude, I'm at, and that explains that is